Alright guys, here's video 4.2.3, and for this video you're actually going to need to find this page that you have, the acidic, basic, and neutral salts page that you have as a handout that you got. Please take a second, find this, pause the video, and read it. If you can't find it, I'm going to leave this on the screen for just a minute, so go ahead and pause the video and read through this. Okay, so hopefully you read that. Okay, let's talk about it a little bit. So really, you are going to need to know the difference between basic ions and acidic ions. So when you have weak acids and bases reacting, they are going to make a salt, right? And so that salt, or the acid-base pair there, is going to determine the pH in solutions. So the salt can be acidic, or it can be neutral or basic. So a salt formed between a strong acid and weak base is an acid salt. For example, ammonium chloride here. A salt formed between a weak acid and a strong base is a basic salt. So here, we are concerned with this problem specifically with basic and acidic ions. The salts are acidic or basic due to their acidic or basic ions shown below. Now remember that bases are going to accept hydrogen ions, so it makes sense that most of these are negative, so they're going to accept hydrogen ions. So let's look at fluoride for an example. So fluoride is going to accept a hydrogen and become HF. HF is a weak acid. F- is its conjugate base. Over here, we have NH4+, so that's going to be able to give up one of those hydrogen ions, and it's going to become ammonia. So it's acidic right now because it's going to give up one of those positively charged hydrogen ions, but then it becomes ammonia, which is NH3. So it acts as an acid in this case. So that's one way you can tell the difference between acidic and basic ions. Okay, that said, have this page nearby while we do this problem. So consider a 0.1 molar solution of sodium acetate. Sodium acetate is a salt. And you can tell that something is a salt is because it's ionically bonded, and you have a positive and a negative there, right? So find the concentration of all the species, pH, pOH, and the percent ionization. We also know, so go ahead and write this in, that the Ka of, let's see, acetic acid, so HC2, H3O2, which is going to be the conjugate acid of that, is equal to 1.8 times 10 to the negative 5, and that's from problem number 3. I just didn't type it here. Okay, so this type of solution, or this type of problem, is a salt problem. So the first thing, you're going to first have to figure out how the ions contribute to acidity. So determine how ions contribute to acidity, or basicity, alkalinity. And then you're going to use an ice box, or ice table, ice box, whatever, and the Ka or Kb, depending on if this is an acidic or basic salt. So let's go ahead and look at that. First thing we always need to do, of course, is to write our equation. So let's look at our equation. So we have sodium acetate, so Na is the plus part. C2, H3O2, goes two ways. This is going to be an equilibrium. Sodium plus your acetate anion. And then ICE. Okay, so what is this salt here? This salt forms sodium, and sodium, as we know, is a neutral ion. So it's neutral because it forms NaCl. That's a strong acid. They don't really tend to do anything. It's formed from a strong acid. Here, your acetate is a basic ion, so it's one of these basic ions here. Now I want to tell you that you won't have these charts on your tests, so make sure you either know how to tell if something is acidic or basic, or you can memorize the chart, but there are other ions that aren't even on here. So that's a basic salt. We have the Ka, we don't have the Kb. So over here, I'm going to write a note to myself. So C2H3O2- is a basic salt. Na plus. Well, that's neutral. We don't have to worry about it. So we're going to use our icebox and our Kb. So we do happen to know the Ka for the conjugate acid of this. So we know Ka for the acetic acid. But we don't know the Kb for the base, the C2H3O2 minus. So the first thing we need to do is find Kb. Okay, so how do we find Kb? We know that Kw equals Ka times Kb. And that's on the back of your periodic table, so you don't need to memorize that. But we do know that Kw, which is 1.0 times 10 to the negative 14, equals Ka times Kb. And so we know this, we can find this. So I'm going to go ahead and rearrange this. So Kw over Ka equals Kb. Plugging in what we know, Kw, 1.0 times 10 to the negative 14. It's a K of water. And and Ka, which is given to us up here, is 1.8 times 10 to the negative 5. So we know that our Kb is going to be equal to 5.6 times 10 to the negative 10. So that's our Kb. And we'll need that after we finish our ice table. Now we can move on with our ice table without having to worry about what the Kb is right there. So I actually jumped ahead a little bit by drawing my ice table here. So I'm not going to draw my ice table for this reaction because this is only the salt reaction. So you can go ahead and erase that because we're not going to use an ice table to figure out how much salts form. We don't really care. Okay. So you can go ahead and erase that. That was just the salt dissociation equation. Now let's go ahead and write the acid-base equation. So since this really has nothing to do with the acids or bases because it's neutral, we're not even going to worry about it. This is what we care about, this basic ion that's formed. This is a salt. We don't care about that either. We just care about the basic ion there. So how does this basic ion contribute to the pH of the solution? Because it does something. So what it's going to do is interact with water. So you're going to have your acetate, C2H3O2 minus, plus water, and water's a liquid. It's going to be in equilibrium with, now since this is acting as a base, of course, it's going to tear a hydrogen ion off the water. Water's acting as an acid, donating that H+, and we're going to form acetic acid. Oops, not H2. There's just one H. HC2. H3O2, that's acetic acid, plus what's left over of my water, which is now just hydroxide. So that hydroxide in solution really is what's causing that whole solution to turn basic. And here's how it's formed. So now we need our ice table when it comes time to calculate the amount of hydroxide in solution. So how much salt did we start with here? Well, this is a soluble salt, so all of it dissociates. All of it turns into Na plus and acetate, right? So we started with 0.1 molar of this, so we're going to have 0.100 molar of the salt. Now remember, liquid doesn't count, so we can go ahead and X that out. This is going to be just a normal ice table, so you start with 0 and 0. We don't know how much this is because this is going to be a weak base, so minus X plus X plus X. So 0.100 minus X, X, and X there. Okay, so now we have our ice table. And now, just like before, we can move on like we have been. So we can write our Kb expression. Remember, we're writing Kb because we're starting with a base here. So Kb equals X squared, so X times X, over our 0.1 minus X. But again, I'm going to ignore that X. So there's our Kb. And we calculated what our Kb was over here, 5.6 times 10 to the negative 10. So that's equal to 5.6 times 10 to the negative 10. So we know now that X equals, when you plug this all into your calculator, multiply and then take the square root, X is equal to 7.5 times 10 to the negative 6. So that's my dissociation. Okay, figuring out all of my different concentrations. I'm going to draw a line here so I can keep these separate. First thing I'm going to figure out the concentrations of all these species that I have up here. So concentration of acetate, C2H3O2 minus equals 0.100 minus X, and my X is 7.5 times 10 to the negative 6. Well, you plug that in and it's still 0.100 molar. Nothing's really changed, so not very much is dissociated. Now I'm going to do my concentration of the acid that I formed. Concentration of acetic acid is just X, so I calculated my X already, of course, to be 7.5 times 10 to the negative 6 molar. Concentration of hydroxide equals X, so 7.5 times 10 to the negative 6 molar. Okay, now that I have my concentration of hydroxide, I can easily find my POH. So POH equals negative log of the hydrogen ion, or sorry, of the hydroxide ion concentration. So negative log of 7.5 times 10 to the negative 6. And my POH should be equal to 5.13. From POH, the easiest thing to find next is going to be pH. So pH equals 14 minus 5.13. And that's going to give me, let's see, what is that? 8.87. That's my pH, which is good. So my POH is lower than 7. It means it's a base. pH is 8.87, so it's not super basic. It's not like those ones that we were seeing before, but it's still a base. It's above 7. Now let's do my hydrogen ion concentration, and that's going to be equal to 10 to the negative pH, which is 10 to the negative 8.87, which is equal to 1.3 times 10 to the negative 9 molar. I'm getting a little squished for space here. The last thing we need to do is percent dissociation. So percent dissociation equals is equal to X over I. So my X is going to be really small, 7.5 times 10 to the negative 6. And my initial amount that I started with is 0.100 times 100 equals 0.0075% dissociated. That's how much dissociated. Really tiny number. So some keys for this here. The very first thing that you needed to do was figure out how this salt breaks up, and you're figuring out the ions that it breaks up into. Are they basic or are they acidic? And after you figure out if it's basic or acidic, in this case it was basic, you figure out how it reacts with water to form acid or base. So if this was an acidic salt, it would react with water in some way by giving off a hydrogen ion, forming H3O plus over here, or just H plus, and it's a conjugate base. So you're just going to make sure that you mix it with water and see what happens with your solution there. And then you go through just like we did before. Exactly the same stuff afterwards, but the key there was just that in the very beginning we had to determine how the ions contributed to either make it a base or an acid. Alright, let's move on to example 6. Consider a 1 liter solution. So we have a 1 liter total solution in which 0.1 molar, again that's vinegar, so make sure you memorize that, and 0.05 moles hydrochloric acid are combined. So here we're combining a weak acid, which is our vinegar, and a strong acid, which is HCl. So this type is weak plus strong acid. So we're not combining any bases here. So what are we going to do? So we're going to do an ice box. Ice table, ice box. And then we're going to use the Ka for the weak acid. Now the strong acid is going to dissociate 100% into H plus and Cl minus. So it turns out that you're going to also have a common ion effect happening here. Because you have this H plus and you already have an H plus in the products over here, that hydrogen ion is now going to be a common ion. So the strong acid is a common ion. And really, we're going to end up seeing that the strong acid will determine the pH. And I'll show you proof of that and why that happens as we do our ice table here. But just conceptually, that makes sense, right? So if you have a stronger acid and a weaker acid, the stronger acid, of course, is going to donate more hydrogen ions. So that really alone is going to determine your pH, because the amount of hydrogen ions from your acetic acid are going to be negligible. So let's take a look at how to do that. So let's do our icebox. Let's write our Ka. So we've been using the Ka of acetic acid. I just didn't type it in these, but we had it in all the previous problems. So let's go ahead and write your Ka there. So next step, always write your equation. HC2, H3O2, that's your acetic acid, and that's going to dissociate into H plus C2, H3O2 minus. Now I'm writing my equation for my weak acid, and I'm doing an ice table for my weak acid because I already know that my strong acid is going to dissociate 100%. You don't even really need an ice table for that. You just know that you're going to get 0.05 moles of H plus, right? So all of these moles are going to be H plus. Okay, so how much acetic acid are we started with? 0.100 moles. How much H plus are we starting with already? Well, even before this has reacted, we have all this HCl in solution, so all of this is going to dissociate. That means we have 0.05 moles of H plus. 0.050 moles of H plus already in solution because HCl breaks up 100%. Although we haven't formed any acetate anions yet because this reaction hasn't started. These are just our initial conditions. The change that happens here, well, we don't know how much of this is going to break up, so minus X plus X plus X. For your ending amount, 0.100 minus X, 0.050 plus X, and X is right there. Okay, so there's our ice table. Next step from an ice table, always Ka. Ka equals products over reactants, so my products are H plus acetate over my undissociated acid. Okay, plugging in my numbers for this. Ka equals my H plus, which is right here. Now the H plus, we're going to go ahead and ignore this plus X because really the amount of hydrogen that comes from this ammonia, or not ammonia, I'm sorry, this acetic acid, this vinegar, is nothing in comparison to hydrochloric acid. So it's not going to come off very much because it's such a weak acid going up against a strong one. So the plus H is 0.050 plus X, and your C2H3O2 minus, your acetate, was just X over my reactant. So my acetic acid, again, 0.100 minus X. So those X's, I'm just going to completely ignore because they're tiny in comparison. And when you take into account sig figs, it's still going to be 0.05 and it's still going to be 0.100. So let's just make our lives easier. Equals the Ka, and we know the Ka for the acetic acid is 1.8 times 10 to the negative 5. So just rewriting this so we can see it more easily. We have 0.050x over 0.100 equals 1.8 times 10 to the negative 5. Plugging this into your calculator to solve for x. X equals 3.6 times 10 to the negative 5. Okay, so that's how much hydrogen ions dissociate. So that's your X here. All right, let's find the concentration of all the species. Just write a line to keep myself separated. So the first one, I'm going to do acetic acid. Concentration of acetic acid equals 0.100 minus X, which is 0.100 minus X, 3.6 times 10 to the negative 5, which is still 0.100 molar. And that's, again, why we could safely ignore that X. is it didn't make a difference. It doesn't even make a dent. The H plus concentration equals, let's see H plus at the end, 0.050 plus X. So 0.050 plus 3.6 times 10 to the negative 5. And I'm sure you can already see what's going to happen here, and that this is 0.050 molar. So notice here that the number of hydrogen ions doesn't really change when you add acetic acid to it. It's all from the HCl that was originally there. It's all from that strong acid. So that's why we said before the strong acid will determine the pH. Let's go ahead and do our acetate. C2H3O2 minus, and that's just X, and that's 3.6 times 10 to the negative 5. Not very many acetates. Okay, so my pH equals negative log of the hydrogen ion concentration, which is 0.050, which equals 1.30. That's your pH. So notice here, I'm going to write a little asterisk. Notice pH only depends on strong acid. SA abbreviation for strong acid. Alright, POH is easy to find from pH. 14 minus your pH, 1.30. It's be equal to 12.7. POH is nice and high. I mean, it's not very basic. Concentration of OH minus equals 10 to the negative POH, so 12.7. And that gives you 2.0 times 10 to the negative 13 molar. Percent dissociation equals X over your initial. So my X was 3.6 times 10 to the negative 5 over my initial amount of my weak acid there, 0.100 times 100 gives me 0.036% of that acetate reacted. Okay, that's it for problem 6.